We are in Chapter 1, Section 2, where we will be discussing stress and axial loads. Earlier in the first 4 sessions, we discussed the background to mechanics of materials. This is the 5th session, and we effectively start the discussion on mechanics of materials. In this session, we introduce stress. This is a roadmap of the first 4 chapters, and here we get a sense of where we are in the overall scheme of things. So we are starting section 2. Here we give a preliminary understanding of the scope of mechanics of materials. Mechanics of materials discuss and study the effect and behavior of structures under different types of loads and different magnitude of loads. Structures are built to withstand loads. These loads may be axial loads, moment, torque, shear, or a combination of these. The study of mechanics of materials can be categorized in 2 ways. As per the first categorization, mechanics of materials can be considered a study of strength, deformation, or stability. Since structures are subjected to loads, one needs to understand the strength of such structures. Structures deform under loads. Such deformation cannot be excessive. Excessive deformation adds to safety concerns. Excessive deformation may result in malfunctioning of equipment as well. Long, slender columns buckle under compressive loads, so we need to study stability as well. As per the second categorization of mechanics of materials, we study Newtonian mechanics or experimental behavior within mechanics of materials. Till now, we have studied Newtonian mechanics only. We have studied external and internal loads till now. As we go forward, we'll study loads applied to infinitesimal small areas or stress. Loads and stress causes deformation and failure, and we'll study deformation and failure. Loads and stress affect stability, and we'll also study stability. Here we discuss the method of sections for arbitrary bodies. We have earlier discussed the method of sections for plane trusses. In order to discuss the method of sections for plane trusses, we initially considered the case of a rope subjected to tension T. So here we will recap the discussion first and then go to method of sections picking arbitrary bodies. So here we have a rope AB and it is subjected to a tension T. C is any point, any arbitrary point within AB. Now if you cut the rope at C and introduce a spring scale, the whole rope still under tension T, then the spring scale will show a tension P. That means that AC is under tension T and CB is also under tension T. And there's an action-reaction force pair that is acting at C. Now instead of taking a section at C, if we consider an imaginary section at C, now C can be any arbitrary point, then at the point C, there's a action-reaction pair acting. So AC is being pulled internally by CB using tension P. In the earlier slide, we discussed method of sections. Till now, we have used method of sections to analyze plane trusses only. Here we consider method of sections applied to an arbitrary body. So this is an arbitrary body on which there are 5 forces acting, and we take the section ABCD. Here we have the 2 portions. Then there will be action-reaction forces acting where we have taken the section. So here S1 and this S1 are an action-reaction pair. If S2 and S2 are an action-reaction pair, and same with S3. The number of internal forces is arbitrarily chosen here. The left portion will be in equilibrium under these external forces and these internal forces. The method of sections can be applied not only to forces like here, but also to moment or torque applied to bodies. A common phrase related to method of sections is, if the whole structure is in equilibrium, then any part of it, considering internal forces, will also be in equilibrium. Before we extend our discussions any further, we would like to mention that we assume that the material we are dealing with when we are considering the different bodies are homogeneous and isotropic. Till now, we have discussed forces only. Thus, we have discussed external forces and internal forces. Here we introduce the concept of stress. In the earlier slide, we took an arbitrary body subjected to forces. We passed a section through the body and considered that there were 3 forces acting on the section. If we consider the left-hand portion of the body, then the left-hand portion would be in equilibrium under external forces and the 3 internal forces. The 3 internal forces can be replaced by a single resultant acting on the section. Here we have a portion and R is the resultant acting after taking a section AA. The portion is in equilibrium due to forces Fa, Fp and R. Now the resultant R is due to small forces acting on small areas throughout the section A. And let us consider a small area del A on the section A, and let del P be the resultant force acting on del A. Then the stress acting would be given as S is equal to limit del A tends to 0 del P by del A. We earlier saw that resolving forces in the vertical and the horizontal direction is advantageous for analysis. So here we resolve del P into a vertical force del F and a horizontal force del V. So del F is normal to the surface and del V is along the surface. Then the normal stress sigma is given as limit del A tends to 0, del F divided by del A. And the shear stress denoted tau is equal to limit del A tends to 0, del V divided by del A. We have thus systematically moved from external forces to internal forces and now to stresses. Earlier we discussed general stress and normal and shear stress at a point in a body subjected to loads. No mention was made of a coordinate axis. We realized that an infinite number of planes can pass through a point. As such, infinite values of stresses can be given at a point. In order to give the state of stress at a point M in a body subjected to loads, we first assign a coordinate axis as shown here. We then consider an infinitesimal cube or cuboid at that point. The cube or cuboid considered has its faces aligned with that of the coordinate axis. We obtain the stresses on the faces of the cube or cuboid parallel to the coordinate axis. These stresses can be normal or shear stresses. We also designate or give a name to the stresses. If 2 points in a body has the same stresses on all the faces in magnitude and direction, then these 2 points can be considered to be identically stressed. We can also compare the stresses between 2 points by comparing the stresses acting on the elements. In order to obtain the stresses on the faces of the element at a point in a body, we use the method of sections. Thus, here a section has been taken parallel to the YZ axis and passing through the point. Here a section has been taken parallel to the XY plane and passing through the point. We'll discuss how we obtain and designate the stresses acting on the faces of an element in the next few slides. We are in the process of defining and designating the stress at a point in a body subjected to a number of forces. So here we define and designate the stress at the point M. In order to do that, we pass planes and represent the general forces acting around a point in terms of normal and shear forces parallel to the axis. We then define the stresses related to the coordinate axis. So here we start with the YZ plane. We have taken a section that is parallel to the YZ plane passing through the point M. Let us consider an area del A about the point M and let the force acting on that area be del Px. Now we can resolve the force into a force that is normal to the plane del Fx and a force that is parallel to the plane del Vx. While del Fx is in the direction of the x-axis, del Vx is not in the direction of any axis. So we resolve del Vx again into del Vxy and del Vxz, which are aligned with the axis. Del Fx is a normal force, del Vxz and del Vxy are shear forces. Now, if we let del A tend to 0, then Sx is equal to limit del A tends to 0, del Px divided by del A. Sigma x is limit del A tends to 0, del Fx divided by del A. Tau xy is limit del A tends to 0, del Vxy divided by del A. And tau xz is limit del A tends to 0, del Vxz divided by del A. We are in the process of defining the state of stress at a point M in a body subjected to a number of forces with respect to a coordinate system. We have already defined and designated the state of stress corresponding to one plane, the YZ plane. Thus, corresponding to the YZ plane, the stresses acting are a normal stress that acts parallel to the x-axis and two shear stresses, tau xy and tau xz, that acts parallel to the y and z axis. We will now define the state of stress acting at point M with respect to the xy plane. So here we have taken a section of the body parallel to the xy plane and passing through the point M. As earlier, we take a small area around M and the resultant force is del Pz. If the resultant force is del Pz, then we resolve the forces into three directions that are parallel to the axes. So del Fz is a normal force parallel to the z-axis, and del Vzy is parallel to the y-axis, and del Vzx is parallel to the x-axis. The corresponding stresses are given as follows. Sz is limit del A tends to 0 is del Pz by del A here. Sigma z is limit del A tends to 0, del Fz by del A, and we also have tau Zx and tau Zy corresponding to the shear forces. In a similar manner, we can take a section parallel to the xz plane, passing through the point M, and we can find a force del Py. So then Sy would be given as a limit del A tends to 0, del Py by del A. After that, we can resolve del Py into three forces, as we have done in this case, and we'll get the corresponding stresses as sigma y, limit del A tends to 0, del Fy by del A. Now yx is limit del A tends to 0, del Vyx by del A, and tau yz. So now we have defined and designated the stresses at point M due to all the three planes corresponding to the coordinate axis. Earlier we found the stresses parallel to the three planes of the coordinate axis at the point M. This diagram shows how we found the stresses parallel to the YZ plane. Thus we found the stresses parallel to the YZ, XZ and XY plane. We earlier mentioned about an infinitesimal cube at point M with stresses acting on its surfaces. Here, a magnified diagram of the infinitesimal cube is shown. This plane of the cube is parallel to the YZ plane. The stresses on this plane is same as the stresses earlier found by taking YZ plane passing through the point M. Similarly, the stresses on this plane is same as the stresses earlier found by taking an XY plane passing through the point M. And the stresses on this plane is same as the stresses earlier found by taking an XZ plane passing through the point M. Now we found the stresses acting on the YZ plane by taking a section as shown in this diagram. However, we could have taken a section so that this portion of the body was there and this portion or the portion to the left was cut off. Then the stresses we would have obtained would be equal and opposite to the stresses on this face. So would have obtained the stresses on this face. Similarly, the stresses on the far face is equal and opposite to the stresses on the front face. And the stresses on the bottom face is equal and opposite to the stresses on the top face. This whole body is in equilibrium and the infinitesimal cube at point M is also in equilibrium. So now we have given the state of stress at point M. We now look at designation. Here with tau xz, x represents the plane. So the first subscript represents the plane. X represents the YZ plane. And the second subscript, here it is Z, it represents the direction. Similarly, in tau yx, y represents the plane. So y represents the xz plane. And the second subscript, x, represents the direction. We now look at signs of stresses. This face of the infinitesimal cube has the highest x coordinate. The direction of stress is same as the x-axis. Then we say that the direction is positive. The case would have been the same if we were dealing with the negative ordinate. This face has the highest y ordinate and the direction of sigma y is same as the axis. So we say sigma y is positive. Again, this would have been the same if we were in the negative side of the axis. Stresses comes in pairs. So for a sigma x here, there's another sigma x on the other side. And signs in stresses are assigned to pairs. So sigma x acting on this infinitesimal cube is considered to be positive, and the infinitesimal cube is considered to be in tension. Here, the direction of sigma x is opposite to the x ordinate. So this stress pair is considered to be negative. As we can see, the stresses are compressive. We now look at shear stresses. Consider a point in the middle of this cube. Then with the orientation as shown, tau xy causes an anti-clockwise moment about the point in the middle of the cube. Similarly, tau xy on the other face causes an anti-clockwise moment. These two tau xy causes a couple acting on the infinitesimal cube. This couple is positive. On the other hand, tau yx and its counterpart causes a negative couple. These two couples are both present here, so the element is in equilibrium. We earlier gave the state of stress at a point in a body subjected to loads. This is the three-dimensional state of stress given. We see that there are 9 types of stresses acting on this cube. Out of these 9 stresses, 3 are normal stresses and 6 are shear stresses. Often in practice, the stress associated with the z direction are not present. So sigma zz, tau zx and tau zy are not present. We earlier mentioned that tau zy and its counterpart on the opposite face cause a couple which is negated by tau yz and its counterpart on the opposite face. So if tau zy is 0, then tau yz is also 0. Also, tau zx and its counterpart on the opposite face cause a couple which is negated by tau xz and its counterpart on the opposite face. So if tau zx is 0, then tau xz is also 0. We are thus left with these stresses acting. These stresses are often given in a two-dimensional diagram. This two-dimensional diagram is common and will often be used in different chapters. We now show a relationship between two of the shear stresses using this two-dimensional diagram. Let us consider the point A and take moments of all the forces acting on this element about point A. Then sigma x dA is a force, but there's another force, sigma x dA, acting in the opposite direction, and they don't cause a moment about point A. Similarly, sigma y dA is a force, but there's a force sigma y dA in the opposite direction, and also they don't cause a moment about point A. This force tau yx dA passes through the point A and does not cause a moment, and this force tau xy dA passes through the point A and also does not cause a moment. The only forces that cause a moment about point A are tau yx dA, the force here, and tau xy dA, the force here. The moment caused by tau yx dA is tau yx dA into dA, and the moment caused by tau xy dA is tau xy dA into dA. Point A is in equilibrium, and as such these two moments has to be equal to each other. That means tau xy is equal to tau yx. So this is the relation we were trying to establish. We have used here a two-dimensional case, but if we were to revert to the three-dimensional case, then it can also be shown that tau xz is equal to tau zx and tau zy is equal to tau yz. So out of the 9 stresses discussed, only 6 of the stresses are independent. One would notice that we used forces to find out a relation between stresses here. This is common in mechanics of materials. Forces are vectors while stresses are not. So we convert stresses to vectors or forces so that vector rules can be used. This way, we are able to establish relationship between stresses.